Welcome viewers to the 17th episode of BeyondPhrenology. Today we are delighted to have with us Chris Kello. Chris Kello is a professor of cognitive sciences at University of California, Merced, also been the chair of the department. He started his journey as a psychology undergrad from University of Rochester, moving forward with a Ph.D. from UC Santa Cruz. University of California, Santa Cruz, followed by a postdoc at Carnegie Mellon. Then he went to George Mason University, if I'm correct, as an assistant professor. And thereafter, he moved with the tenure to University of Merced, California, where he currently is. Chris Kello does very interesting stuff, especially in the boundaries of eco-psych, neuromorphic computing, and he has some own models of which he has developed himself of neural networks, which I guess he are also patented. He is on the board of advisors of several technology companies, and a kind of a future thinker when it comes to where neuroscience can lead to computing. So, Chris, welcome to the show.
Madhur, thank you so much for having me.
So, Chris, I don't know whether I did justice to the very interesting and very non-linear career trajectory you had, and the work in several domains, and very influential work you have done in several domains of psychology and neuroscience. Would you like to walk us through, how you ended up being a professor in this department in this area, and like as an avid programmer and a technology person, you are in the psych department. So what's the connection between psychology, neuroscience, and computing?
Yeah, sure. Well, thanks again for having me on. I guess you could say it started when I was an undergraduate at the University of Rochester, and I was fishing around for a major, and I found this thing called cognitive science. They happen to have it. This is way back in the late 1980s type of thing. I think they might have been one of the first universities to have a cognitive science major, and I thought this is great because I was already interested in AI and computers, but I didn't want to just be a computer programmer, and I had wide-ranging interest to this day, and so cognitive science really fit my kind of personality. I started working in Mike Tannenhaus's lab. He's a psycholinguist, and we were doing work on online sentence comprehension. And so if everybody knows what I'm talking about, if you're reading a sentence as you read along, sometimes you will sort of misunderstand the sentence. You go back. You have to, it's called a garden path. You retrace your steps to try to figure out what you're reading, right? And so that was the kind of psychological process that I was involved in, my undergraduate thesis, doing that kind of research. I came upon a paper in neural networks, distributed model of lexical memory, lexical semantics. I think it was ambiguity resolution, so how people resolve the words that have different meanings, how you sort of figure out which meaning goes in a particular context. And it was by a guy named Alan Kawamoto at UC Santa Cruz, and the light bulb went on for me at that moment. It's a very clear, memory for me where I said, that's the way I want. That's what I want to study. I had a concentration in AI, and specifically natural language processing. And I say this because it's funny. Here we are with ChatGPT. Back then, I thought the natural language processing was kind of way too toy-like, not nearly powerful enough to do actual language comprehension and production, which is why I got more into cognitive science. And when I saw connectionism, I thought, wow, I don't know, none of us really know how the brain works or how we process language and all this kind of stuff, but this has got to be somewhere on the right track. And so I went to grad school to work with Alan Kawamoto at UC Santa Cruz. Again, fast forward, I'm stunned by what's happened to the world of natural language processing, connectionists, now deep learning, now transformers, now ChatGPT. That was 30 years ago. I can tell you that I never, ever, ever would have expected to see what's happened today in my lifetime. It's shocking. Anyway,
it's just exponential.
Go ahead.
The advance has been exponential.
Totally exponential. Really, even as of deep learning kind of really got its, ahead of steam around 2012. Even around then, still natural language processing, the idea of an AI, it was still hard to imagine.
Right.
Very, very hard to imagine. So
Yeah,
anyway,
it's so interesting that there are certain fields in science where you read some articles published like in 2020s, and they would cite an article in 1996, and they would say recently, and then you look at the gap, what has been advanced in the 25 years is like insignificant, almost very similar kind of work.
Yeah.
And then you have fields like natural language processing and neuromorphic computing, and you have the same 30-year span. And I mean, things which are like 2 years old are like look ancient.
Ancient, absolutely. It's so true. I mean, like you said, exponential. The growth is truly off the charts, and I don't know where it goes from here. I don't know if anybody does, but it is.
Yeah.
Well, we'll get to neuromorphic engineering. I think that's probably one of the multiple sort of futures of AI is really to think seriously about the hardware, about energy constraints, the physical constraints on language processing.
Yeah, this is something we should definitely cover, as we move on. With the introduction,
But I can, if I may go back real quick.
Yeah, of course.
So I spent the first chunk of my career both as a graduate student, then as a postdoc at Carnegie Mellon, and then to some degree as an assistant professor at George Mason University, where I was really focused on psycholinguistics, models of lexical processing, so reading words, deciding whether a letter string is a word or not. Back then, that was kind of the Drosophila of cognitive science in a lot, or at least certain areas of psycholinguistics. Just how do you process individual words? I
like how you put it, the Drosophila of cognitive science.
Yeah, I've used that in a couple of grant proposals back in the day. So yeah. That was, and it was just something we could get our hands on and study and build models that could reasonably process a few thousand words. That's the technology sort of possible.
What kind of models and what kind of processing?
Yeah. So these were what we used to call connectionist models. They are at their heart, very similar. A lot of, the same types of mechanisms that you see in deep learning, transformers, et cetera, today. Early days, there were Hopfield models, and I don't know, if your audience is familiar with that. But so one of the things that I was very interested in from early on, which is also going to segue into the more ecological psychology and dynamics domain, is recurrence and dynamics in neural networks. So one of the first kind of networks I actually worked with as a first-year graduate student, Ph.D. student in Alan Kawamoto's lab was a version of a Hopfield model, which is basically a fully recurrent model that has enough constraints on it that you can measure things like the energy landscape of the model, and it will have a well-behaved attractor dynamic where it will go to a point attractor, follow down into a basin, and you can do interesting work on relating attractor dynamics to what we see in the dynamics of human behavior, in this case, in the dynamics of people reading words. And so early day, way before I knew anything about, again, I'm foreshadowing here, 1/f noise or ecological psychology. Of course, that was around, but it wasn't on my radar. I was working on dynamics. And so we also, though, and I will say, pretty quickly after that first year, we started building models that were not dynamic. And the reason was that dynamics are hard.
It is hard, yeah.
Non-linearity is very difficult to work with. Take a lot, they're computing intensive. And back then there's not, having the computing ability to work with those models is very limiting. And again, this is interesting because that's also where deep learning ended up. Decades later, but recurrence is great and interesting, but you end up doing something practical. So you do feed-forward networks. It's always backprop or some kind of, online learning algorithm that you're working with. We're always working with distributed types of representations where, you can use those representations to learn up based on experience and generalize to something new. So that's never changed. And you just try to keep it as simple as possible. Well, that back and forth between recurrent dynamics and feed-forward and lack of dynamics, feed-forward processing, went on since, I don't know, at least the 70s, 80s, and then all the way through to transformer architectures today, where one of the big wins was we can figure out how to get the right kind of context and we can replace dynamics, which until very recently was still, if you know about long short-term memories, we can replace dynamics with feed-forward, and that will make things work. So back then, that's the kind of, we were also working with feed-forward architectures after that first year of dynamics. Shall I continue down to,
Yeah, of course, of course, of
make my
course.
way to one over F?
Yeah,
No, I won't, I publish a lot and I have an identity. I often say I'm a card carrying word nerd. To this day, I still have word nerd tendencies in me. That's a sort of, a group, a sort of a sub community of psycholinguistics of these
yeah, yeah.
people who really focus on words. And I did
It's
a
a
lot of
fascinating area. It's a fascinating area. Even now, if you go back into psycholinguistics, it's
yeah.
extremely. It's like it just sucks you in. To be honest.
Yeah, it sucked me in, that's for sure.
Yeah, yeah,
Again, it was just tractable, and it's again. I will go back to the Drosophila metaphor.
yeah,
You can really make progress by these models. We could understand. We could run experiments, make predictions,
yeah.
account for the data to some degree. Whereas at the sentence level or at that time, anything larger, it was just not possible. We didn't have the models to do it.
Right.
I can remember again foreshadowing what was to come. One computer science student at Carnegie Mellon, Doug Rohde, he was starting to work on sentence level models. And it was just barely, and he was the best. I mean, in terms of the ability to use what computing power we had to do sentence level processing,
Yeah.
barely could do it. That was just coming online, and that was 1999. So
And this is about
yeah,
this is at CMU.
that was that. So I'm jumping ahead. That was at CMU. That was at
Okay,
CMU.
okay.
Right?
And this is also the
so
time. Yeah,
yeah. My life as a word nerd
yeah,
basically went right through graduate school and right into CMU.
yeah.
All that time, I was straight up connectionist modeling,
Right.
psycholinguistics, always combining both experiments and models.
And,
Like a lot of my papers have both.
And CMU was kind of an epicenter of this kind of work during that time, right? And the cutting edge.
Yeah. I worked with Dave Plout, who's a fabulous and let me just shout out to all my mentors. They've been incredible. Starting with Alan Kawamoto, who was just a wonderful guy, gave me the space and the guidance. He was a very hands-off advisor, and I think that's worked with me. So we worked very well together like that. Dave Plout was more hands-on, but really sort of opened my eyes to the big world of science. So Dave Plout was, like you say, and Jay McClelland was there also at that time. Jonathan Cohen was there. And these are people who are big names in that world of connectionist modeling. And so going to Carnegie Mellon was, again, UC Santa Cruz was great, but it was small and somewhat isolated. You have to go it's far to get there type of thing.
Right.
And here I am now at Carnegie Mellon and University of Pittsburgh. It was a joint effort, something called the Center for the Neural Basis of Cognition. So by the way, that's when I also started to get more neural, was also at Carnegie Mellon. And now all of these, big names in the world of cognitive science are coming through on a regular basis. And Dave Plout was very much my mentor and took me under his wing to sort of introduce me to this much larger world, which was fabulous. And of course, Jay McClelland and many, Brian McWhinney, I should give a shout out as well, another mentor of mine over there.
So you have worked with the best minds of that time. Yeah.
Well, I've been very lucky.
Yeah.
Extremely lucky. There's lots of best minds, I'm sure you know. There are lots of different communities, and some of them I don't necessarily intersect with, but I'm just extremely fortunate to have intersected with a number of great minds, including all of those. And then if we want to start to make that transition to the dynamics in one of our F world, when I was a graduate student, I met Guy Van Orden. He came and gave a talk and blew my socks off. And it was this connectionist talk, dynamics, very dynamics-oriented connectionist talk. I think at that time, if I remember correctly, Guy had not yet spent a year at the University of Connecticut working with Michael Turvey and everybody else there, and really sort of made that transition. Of course, he was going in that direction, but
And where was he at that time? Where was he at that time?
Arizona State.
Okay.
I'm pretty sure he was at Arizona State when he came and gave that talk. Must have been probably my last year of my Ph.D. Anyway, so I met him, really liked him. We spent a lot of time together, but then we part our separate ways, and then he's, I don't see him, and then he comes back, and in that interim, he spent a year at, I think it was a sabbatical at Connecticut, and started doing this one of our stuff. And in that same time, independently, I happened to see a talk by David Gilden, another big influence, not a mentor of mine, but I know him, and he changed a lot for me. Both Guy and David Gilden were the two of the main, and then of course Turvey a little bit later. But first it was Guy and David Gilden. I saw him give a talk on one of F noise. It was when that science paper, I think it's 1996 science paper. So he was giving the talk before the paper came out at Psychonomics, and it was a packed room. And again, it was just another one of those moments, just like when I read that connectionist modeling paper from Alan Kawamoto.
And it's a very attractive title, right? Cognitive emissions
Yes.
of one
Yeah,
bias
they
noise.
even
Yeah.
the cognitive emissions, I think that's a psych review paper.
Okay,
maybe?
so this is the previous one, yeah.
This is a science. This is a science article where he does the and I'm sorry, I'm talking we know this field.
Yeah,
for your audience.
we cite it every time, but it's just not coming, to the mind right
sure.
now.
And I don't and I know I'm probably saying stuff that your audience does not necessarily know what I'm talking about.
I'll post a link. Yeah.
We'll talk a little bit more about one breath. But anyway, here's why the light bulb went on for me. So remember, I'm a word nerd. I'm dealing with long lists of responses.
Yeah.
Often hundreds or even thousand-ish responses to words. And I'm looking at these data, and I'm steeped and I'm immersed in these data. I'm using these connectionist models to understand the data. And we can only explain a small proportion of variance. And that's, typical of psychology and psycholinguistic type of data. You're lucky if you get 10, 15, 20%, 30% is amazing type of thing of the variance with whatever you're doing with your models. So what's all this leftover variance, right? And the assumption is simply that, well, it's noise, it's garbage, it's whatever, it's stuff you can't explain, let's not worry about it type of thing. Okay, there's probably some dependencies in there, but nobody ever thought of them as long-range dependency. They just think, well, maybe there's some influence of the previous response on the next response, but that's about the extent of it.
Right.
But as an experimentalist, working with these models, knowing their shortcomings in terms of seeing my own data and realizing how hard it is to explain any of this variability, I see David Gilden, and the light bulb just goes. I'm like, oh my gosh, that's where the action's at. Is in all that data that we get that we cannot understand actually does have structure in it, and it's something called, I'd never heard of it, something called one-over-if noise.
Yeah.
And I thought I need to understand this. I even remember, I shouldn't say. I'm going to say one of my mentors happened to be sitting with me in the audience. Of all the mentors that I mentioned, one of them was in the audience, one of the modelers.
Yeah.
And after the talk, I turned to, they're all male. So I turned to him and I go, oh my gosh, what did you think of this? And he was very dismissive of it. And I thought, why? I didn't and to this day, I can understand why, but I find this fascinating. Because it is you can see there's a break in these communities. And it was right at that moment.
Yeah,
like sitting right next to me, and I'm blown away by this talk, and he's not, and I didn't understand. I'm like, but wait a minute, we were looking at the same data, right? Like,
right.
Not that this is going to explain all that variance, but at least gives us inroads. It gives us some ability to start to approach these data that we have. And I was already open to dynamics because I already mentioned hot field models, and so dynamics, and this idea of now we have a dynamic that's running through the whole experiment that we need to understand. And so
if you can simplify this, we are talking, what we are talking about here is, for the audience, it's not the trial or it's not the response that matters. It's like the whole experimental session, everything which is happening is connected.
Correct.
And what you're looking at as the variation which you're not able to explain, that has a structure which unfolds over the whole experimental session.
That's right.
Or the whole session.
Yeah. Thank you for clarifying that for our audience. I appreciate it. Yes, and I'm not getting into the mathematical details or the statistical details yet, but as you say, it runs through the whole experiment. That there's something coherent in that dynamic that made some sense to me, and we need to understand it, type of thing. And then that's when I don't remember exactly, but somehow bumped into Guy Van Orden. And he'd also been starting to work on this stuff, had met Michael Turvey and the like. And so we both hit it off because we're both doing the same thing. We're both making a transition from connectionism, psycholinguistics, word nerd. He's very famous for his Rose is a Rose paper, if anybody knows that, homophones and so on. So we were fellow card-carrying word nerds, and now semi-independently, we're both making this transition. Me because of David Gilden initially, Guy because of Michael Turvey and the like. And so now, okay, we definitely need to start working together. And I think somehow right about then is also when he became a program director at the National Science Foundation. And I had just moved to, and I think it was right around the same time. So like so many things in life, it's serendipity,
Right.
things just kind of happen. So in this case, he moved to National Science Foundation to direct what he renamed as the Perception Action Cognition Program. Perception action, very much obviously getting in the eco stuff into the name of the program. And I was moving to George Mason University, which is like 45 minutes away, just down the road from National Science Foundation. So we started hanging out. And, because we're both interested in this one of ref stuff, and we're both talking about it, and we're both local,
Yeah.
So we spent a lot of time together, drinking beers. If you know Guy, that's what we do. And talking science.
Right.
Just like what he did a lot with Michael Turvey and pretty much everybody he encountered. That's what he loved, and I loved it too. Was and so we started collaborating, and he his what I would say very now famous paper. I don't remember the timing at all, but came out right around then. Oh gosh, I'm forgetting the name of the paper, but it's with Turvey and Holden, and it's the very famous, where they really introduced the approach to one of ref noise from an ecological psychology perspective to the more standard, or I don't know, experimental psychology and cognitive science audience. My apologies, I'm forgetting the title of the paper, but in any case, right, all that was sort of happening right around then. So so anyway, so that's how I then started pulling away from the modeling.
Yeah, it's called human scaling, human cognition and one bias scaling, 2005.
Yes.
Yeah.
Thank you very much. 2005, exactly. And so that was, so he was working on that paper when we were hanging out, because we were hanging out prior to 2005. I got to George Mason 2000-ish, 2001. Right. And in those few years is when we were hanging out. So anyway, so the modeling, I was still working on the modeling. I was doing both for a while. My students at George Mason University, like Dara Sibley, for example, we're still working on and by the way, interestingly, getting those models to be bigger and bigger. So by the time I stopped, Dara had put together a model that was about 70,000 words, which at the time, both monosyllabic, bisyllabic words and stuff. So it's, again, interesting. We knew scale.
Yeah.
And we could tell that, right? Scale was going to be important. And so we worked very hard on getting those models to scale up. And it's not just a question of computing power and memory. It's also a question of representation and how you structure the words in the model so that you can handle more of them, and ones that are more variable in their length and all this kind of stuff.
Right.
So again, that foreshadowed where, of course, the rest of the world in the more computer science area, scale became everything, right? And now data is, there's a phrase, data is king, right?
Yeah.
The data it's the size of the model that matters a heck of a lot. We kind of knew it back then, but that's all we could handle. And I decided that I wanted to spend more time and really focus my career on the dynamics, the one of ref stuff and all of that. So at some point I really made that transition, throughout my professorship at George Mason University, and really worked more on the dynamic side of things. So I'll pause there. I mean, I can, so there's there are multiple stages to this. Probably when I moved to UC Merced, and then Neuromorphic engineering and so on. Yeah. But is there anything
you are yourself
before I make that next jump? Yeah.
So you yourself are associated with NSF for some time, right?
Oh yeah, so right. So Guy was there, so program directors at NSF, there are both permanent and rotating program directors, about roughly half and half, and it's a really good model, if you ask me. Guy was a rotator, so he was done after 3 years, and he wanted somebody to succeed him. And of course, I just told you, we're hanging out, we're doing all this work. I'm starting to really get into the perception action sort of side of the business. I think probably at this point, I probably gone to University of Connecticut, met Turvey, met the whole crowd of ecological psychologists, very amenable. It might have been, timing, I don't quite remember, but right around then. Anyway, so Guy twisted my arm, and he really did have to twist my arm 3 times. I remember because I was an assistant professor. I'm just like, I'm just doing my thing, teaching classes, got my lab going, got a couple grants, just doing the right thing, did what assistant professors should do to get tenure type of
which
thing.
I'm trying to do right now. Yeah.
I'm sure you're doing great, madam. I'm sure you're doing great. Yeah. Yeah. You're in your first year of assistant
Yes.
professor, right?
Yes.
Yeah. So you get it, right? So imagine if somebody came to you, like, I don't know, Aaron Likens or something, comes to you and says, "Hey, why don't you go be a program officer?"
Right.
Right in the middle of you trying to just like be an assistant professor, right?
Yeah.
So of course I said, "No, Guy,
Yeah.
thank you. That's very kind of you that you would think so highly of me, I guess." Although in retrospect, I don't know if he was thinking. I think he was just looking for somebody to carry the torch. I just happened to be there. I don't think anything else. Anyway, so I said no, thank you.
Yeah.
And then he did it a second time, a little bit more forcefully, and I still said no, thank you.
Yeah.
And he just wouldn't stop. It was like, I don't know, maybe after so many beers, he wore me down. And I just said, all right. I don't think I'm going to do this, but I'll apply. Yeah, so I applied.
Yeah.
And I got that there's a bug that you can get around NSF and maybe other federal agencies too. It's like it's big science, but you get an incredible view of the field. I had no illusions. It's not like you can have a strong impact on exactly what happens. Yeah, you're like an editor, right? You're making you're getting reviewers and you're making decisions.
No, but maybe Guy Warden like saw the energy and like the vision in you, especially given that you were sympathetic to the cause, to the more dynamic the origin and the dynamic ideas of the brain. So probably that was the reason.
Yes.
Yeah, he could see
for sure.
Yeah.
For sure. No, that you're 100% right.
Yeah.
Mater Guy was, a believer, and he really wanted to make sure that the dynamic side of cognitive science continued to be represented. And to be fair, you can't focus the entire program on that. And I had interest well beyond the dynamics. Remember, I'm still a word nerd and all that.
Right.
But he wanted to make sure that didn't go away. And so, so that's why. And maybe the energy and stuff. And I guess it turns out that I'm not so bad at that stuff. It was a huge learning curve. I did it right when I put my tenure package in. So I remember when I got tenure, I couldn't even celebrate because I was just immersed and steeped in being a program officer and learning how to be a program officer. I was like, oh, that's great. I got tenure. I got to get back to work. I have no time for thinking about tenure right now.
Yeah.
I've got a million things and there's a lot of pressure and, a lot of money involved and stuff. So, but I look back on those days very fondly. Again, I got to thank Guy. Peg Barrett was the division director at the time. She was amazing. She was my boss, I guess you could. And you do kind of have bosses sort of at NSF. She was an amazing boss, very nurturing of the whole program and of me, and many others. Wanda Ward is another one. David Lightfoot was the SB director. So again, what I'm trying to say is it just opened my eyes even more. Right.
At a very young age, you saw like much bigger picture in science, which you
much bigger
don't
picture.
see as a running a lab.
Exactly.
Yeah.
I was involved in the Science of Learning Centers as well, which was like one of their biggest, $10 million award type of thing. And there's the program officers are a lot more involved in the management of those, and I got pulled into that. Fascinating, big science in our field, from a number of different perspectives, and really great. But again, it's not like I knew I was a rotator. It's not, I didn't want to keep doing this. And on a personal note, when I was in UC Santa Cruz, I met my wife, at that point, and still my wife to this day. And she's a Californian, and I love California too. I'm from New York, but I like she's got a big family. I have a little family. So we were always keeping our eyes out for a job back in California that would make sense for me. And so right at the end of that stint as a program director, this job at UC Merced came up. And it was going to be, of course, at the time, UC Merced opened up in 2005. This was in 2000, the job was starting in 2008. So the search was in 2007. So brand new, truly pioneering. Sky's the limit. Blue, you could just imagine, hey, we're going to have a University of California campus here in the middle of California in the Central Valley. And the people who are there at the beginning are going to be the ones who actually make this thing happen and build it from the ground up. Teeny Matlock, another colleague of mine all the way back from Santa Cruz, was one of the founding faculty here. Dave Knoll is a connectionist modeler who I met at Carnegie Mellon, who was also one of the early faculty members. So I knew both of them. Michael Spivey was somebody who I'd met. So all these weird connections, again, serendipity, things like that happen. Michael Spivey was somebody who, strangely enough, the very same year that I went from Rochester to Santa Cruz, undergrad to PhD, he did the reverse the very same year, and into the same lab. He went from undergrad at UCSC to PhD at Rochester to work with Mike Tannenhouse, and I was working with Mike. So like I knew him from way back then, and he was just starting at UC Merced, and they were hiring a lot, and so there was just a lot of excitement, if I dare say, on both ends for me and for them. It was like, this is perfect. They were looking not only
it's also a different way of looking at career, right? A lot of times we try to strive to go to the most established departments or the most famous ones, and here you have an opportunity just to make new things.
Exactly. And again, it was kind of my personality to going off and doing one over F was really sort of a pioneering type of thing.
So what exactly is one over F here? The audience needs to know, like
yes.
So what is F and what is 1 over F?
Okay. So if you take any time series and you're now if you look at that, you can think of it as a waveform, a dynamic. It's numbers that are changing over time, whatever they might be. You can break down that time series. You can move it into the frequency domain. So when you look at it as a time series, we'll call that the time domain. You can now break it down and do something called a spectral analysis. You can do a lot of different things, modern, of course, as you know, but spectral analysis is a nice, instructive way to think about it. Still the way I tend to think about it. So you can decompose that time series into cycles of different frequencies, sine waves, cosines.
Which is our typical FFT, the idea of FFT,
Yes, and that's where frequency, so I'm getting to the F, right? So the F would be the frequency of those sine waves that you would need to construct, or to basically that a signal is composed of, that the time series is composed of. Okay, so that's just called a Fourier analysis, spectral analysis. Mathematician Longo is very famous for showing that any given time series can be completely moved back and forth between the time domain and the frequency domain. So you always represent the data in the frequency domain or the time domain. Now, what's interesting about the 1 over F thing is that there can be a relationship in the time series among those cycles, among those frequencies, such that how prominent they are, and now technically the power of each one of those cycles is inversely related to their frequency, and hence the 1 over F. So in English, what that means is that you've got large, low frequency trends in the data, waves, if you will, that will run through the data over long periods of time. And nested within those, you've got faster but somewhat smaller, because of this inverse relationship, trends running and nesting alongside or in combination with the lower frequency trends, and so on to higher and higher frequencies that are nested within the lower frequencies repeatedly, and hence you get the 1 over F relationship. And there's, Madhur, better than I do about endless ways that we can think about this through different lenses, such as detrended fluctuation analysis. We can think about it in terms of a fractal. We can think about it in terms of a power law. And these are all valid and useful ways to think about the phenomenon. It tends to go by the name 1 over F because of the spectral decomposition.
And what's its relationship with psychology?
That is up to debate. It's a short answer. That is sometimes fiercely debated. And
we should go into that debate between you, Van Orden, and also the Dutch group.
Okay. You want to do that now? That's what I was sort of referring to, right? And not just, when you say the Dutch group, I assume you mean Wagenmakers. And the like. And Simon Farrell was part of that group, and a number of others. they also kind of come from a diffusion group, and like Roger Ratcliffe would also be in that camp type of thing. So it's just so there's not just the Dutch group, but in any case, the bigger picture is this relevant to psychology because it's telling us something about cognitive processes, or is it a type of noise that is, so that people use all sorts of words: spurious, epiphenomenal, in the noise term, uninteresting, not some low level physical byproduct of something, maybe some kind of relaxation processes. So in other words, some kind of decay processes,
some dissipation,
and on and on. So there's all these ways to think about it that you can put it aside, and you can just say that's not the domain of psychology. It's not the domain of cognitive science. And to this day, I think the argument. You certainly can walk into psychonomics conference or cognitive science conference. If people have heard about it, I wouldn't hazard a guess, but a good proportion, perhaps even the majority, still might be like, well, I don't know.
A good proportion,
Let's say a good proportion. It'd be interesting to take a survey. And so, and look, it's so interesting. This is much more this sort of like the sociology of science. Why you get these different kind of
it's very interesting.
It is very interesting. Different personality types involved. Because you look at the same data and you take very different things away from those same exact data. Oh, and now, of course, I should say on our side, if I may, we say, well, it's the majority of the data. It fluctuates with cognitive variables, so it's affected by cognition. There are theories going back, outside from physics, something called self-organized criticality, edge of chaos type of dynamics, where you can kind of make sense. You can hypothesize about how it would matter for cognitive processing. And by the way, I would say what I've seen happen since those early days is that neuroscientists, physicists who become neuroscientists have really run with this idea that there's something important about that noise to help us understand neural function, cognitive function. For us, it was very much understanding the behavior itself, right? From more ecological psychology, where you really focus on the behavior. But in all these cases, you can make the argument, and again, I know I'm waving my hands because there's a lot of technical stuff here, but you can make the argument that it matters. That it's actually, it's very central to understanding what's going on. And that debate has been, and by the way, it's interestingly, there's always this general stand outside of cognitive science and psychology in the sciences writ large. There are people who are just generally dismissive. I would say in general, because they'll go, well, there's lots of ways you can get 1/f, and so I don't know why it's such a big deal. That would be the more general. Maybe you can find people like that in biology or in physics.
But the thing is, I mean, just because the same natural laws can govern some behavior. So, for instance, when you look at the propagation of cracks, like you have some soil, and when the soil kind of dries up, you see these cracks appearing, right? Fractal kind of curves, right? The same thing happens in the skin if you don't moisturize the skin, right? Very similar kind of phenomena. And it's coming out of self-organization and principles of how physical entities interact, right? Now, one can always give an argument, I mean, with the same kind of rationale, right? Like, it's something else, just because it's showing the same pattern doesn't mean the mechanism has to be same or something, right?
That's right.
But that turns out to be not true. There is actually a continuum between, among these processes.
Absolutely. Again, Mater, you know more than I do about this stuff. And so, but I'm with you 100%. Again, it was never in doubt for me. And this is, again, why I think it's partly, if your mind is open to it, based on whatever it is about who you are, your experience, your personality, then it's very easy to go down the road that you just described and just go and see the importance and the relevance of it and not get hung up on the details. So I think that's a big part of this, is that you have to be, I think it's helpful to be a kind of person who can not get too focused on the specifics and the details and get siloed down to, I study this particular model system in this particular domain, and I'm just an expert in that, and I'm not interested in stuff that cuts across domains and whatnot.
And that's where
Some people,
Drosophila comes in.
And a reductionist sort of version of science,
Yeah.
and science, even without invoking reductionism, I mean, just science in general has trended, in Western science at least, towards more and more specialization, more and more specific. You become an expert in a very narrow field, and you're rewarded for that. And there's a lot of, without going into the sociology of it, there's a lot of reasons why that's a great thing to do, and solid, and maybe you can say safe. It's a safe thing to do. But we do need people, I would believe, and this is now like almost my NSF hat on, right? So when NSF, if you're looking at the bigger picture here, you go, that's great, but we also need some science that's cutting across, that's synthesizing, that's looking at bigger picture trends.
Yeah.
Not to, disparage or ignore the details. Those are important too. But we all, always, these are both, we have to do both. As a community, we have to do both. That would be my argument.
Yeah.
Now putting my big sort of big science administrator type of hat on. And so, yeah, and I think to this day, that's the divide. It's the people who are really, skeptical of any kind of science that's not narrow, focused, expert in a particular domain, and that's the way you make progress, versus the people who are like, the way we make progress in big theories is by synthesizing and looking across and finding trends and drawing analogies. And
so 1/f, the idea of 1/f, and almost everything which comes out of this, right? Like what I do is related to it. So 1/f is a more simplistic model, but I would say the whole idea that noise has a structure and it has to do something, and we can manipulate that structure as well, use it for biomarkers. We can play around with it, and
that's right,
and do a lot, with the noise, or basically time series, right?
That's right.
So, how does it cut across the idea of this? Given that a lot of our audience and the whole idea of channel to begin with was eco versus non-eco debate, and you are coming from a background where you were into before complete representational models like psycholinguistics,
right?
And this 1/f noise has not been adapted by that community. These 1/f ideas are more adapted by eco-psych people, right, to explain more dynamical behavior rather than symbolic behavior, which comes in the psycholinguistic domain. So where do you stand on that? Like, do you consider yourself first of all an ecological guy, or like a more connectionist and
this is where and I'm not just trying to be diplomatic here. I'll be honest, because I've had these debates in Turvey's pub till 3 a.m. many times. And so anybody who's met me at one of those meetings would knows where I stand on this, which is honestly somewhere down the middle. I can put my feet in both camps here and understand and relate and appreciate. But I'm not, so I'm a little weird in that regard, in that I haven't gone full bore anti-representation. And again, maybe we need to talk a little bit more about that for at least some of your audience. And yet I very much appreciate the rigor and the attention to the behavior that I believe the ecological psychology perspective brings. So if we go back to the 1/f, and remember what I said, like, here it is, all this in our data, and we're ignoring it. And one of the things I just really appreciated, and to this day really appreciate about the ecological psychology community, is that the data are paramount. The data are what we are our ground truth, what we must always respect and pay attention to. And there's this Turvey's famous for saying no loans on intelligence type of idea, and you don't want to go too far in terms of your theories and abstractions away from those data. I get that, and I really appreciate that discipline. Let's put it that way.
You have put it very well here. So I think a lot of computation, divide between the computation and the dynamics, if you give them the same time series, would be that we will be defining more in terms of the properties of the time series itself. It will be more descriptive. The details are in the data itself, compared to a much kind of a transposition of that data into some other explanatory space, which comes with the computational ideas and interpretations.
Yes. So absolutely. Another way to think about this is that if you go fully in the other direction, past connectionism, all the way to like Chomsky or something, or computational theory of mind, Jerry Fodor,
Right.
again, I don't know if your audience is familiar, like early days of cognitive science to this day, it's completely non-physical. It's completely theoretical. Generative linguistics is at its heart only makes contact with the data at this, at the level of an entire language, and the possible sentences that may or may not be spoken grammatically in that language. That's it. And after that, you're totally theoretical. You're in a completely computational or symbolic mathematical space.
Yeah.
Great. I mean, we need. Sorry. I should take a step back. I am of the mind, and not everybody. I am of the mind that I think we need that kind of thinking. I'm also, so I can easily put myself in that camp and say, I do believe that there are abstractions like symbolic models or computational models that are very helpful to our thinking in so many ways. There are abstractions, like all models are wrong and some are useful, famous quote. And I can look at those and say, there are some very useful models. By the way, including Chomsky. I actually think that there's something to the concept of merge and recursion that Chomsky's more recently sort of known for. In fact, Mater, about the paper where I'm making a relationship between Warren noise and merge and recursion, believe it or not. So if you keep your feet in both camps, I think you can start to see there's value, and there's even knowledge is value in each camp, but there's actually relationships. But you have to take a huge. It's a big bridge. You have to take a big sort of stretch to go from Chomsky to one of F. Okay, so, but that's how I've always been. I mean, so I wasn't working on symbolic models. I was working on connectionist models, but they're computational. They're representational, like you said. They're abstractions. So they might have dynamics in themselves, like a Hopfield model, and that's great. But they're still ultimately abstractions. I think you need that too, in my mind, for the field of cognitive science, I should say. Not ecological psychology necessarily, but if I take a broader perspective, again, my NSF type of hat on here, and I've always thought of myself from the very beginning, right? That from that Rochester day when I met, I should have mentioned Gary Dell. He was my first advisor there, who he's also a psycholinguist guy, ended up at Urbana-Champaign. I knew as a cognitive scientist, like I am a cognitive scientist. And this is what I think it means to be a cognitive scientist is somebody who's willing to try to pull from these different fields and see, pull together and synthesize. Right? Not all cognitive scientists, certainly not all cognitive scientists see themselves that way.
Right.
I do.
So coming back to 1/f noise, I mean, cognitive phenomena, neuroscientific phenomena, all behavior has 1/f noise, no matter how you measure it, no matter, what the context is, right? And within that 1/f, you can have a variety. And if you go into more multifactorial domain, you can see a much more nuance and texture within that, right?
Absolutely.
Now, the question is, one of the criticism is that, it's there and it will be there.
Mm-hmm.
So, if you put in those models, it has some predictability, and that can also explain some amount of variance.
Right.
So next what? What do we do with that? Can we actually use 1/f noise, or generally, these nonlinear properties? I mean, 1/f is more like a linear approximation, but linear and more nonlinear kind of noise analysis. Or something more than that. Can we use it to create neural networks?
Yeah. Short answer is yes. It's been done. Usher and Marius Usher, who I know, and I can't remember the Salami. I'm sorry. So a long time ago, early 90s, was already doing exactly what you're asking. I'll explain in a minute. Kwok and Smith, 2004. Bershinger and Notschlager, 2004, about the same time. So. And ever since, and I'll explain what I'm talking about in just a minute, but I want to start by saying what you were saying has been done and started to be doing was people working on it quite a long time ago. And we sort of, and I love that literature, and I've been trying to pull it into my own work through, if we get to the neuromorphic engineering, that's sort of, there's a path here.
And we should also navigate towards bring in the critical branching neural networks.
Well, that's exactly right. So that's what I mean. That's the path. The path is critical branching to get from. So, but to go back to these other authors, and Langston, so Santa Fe Institute, right? Complexity science was a bit, there's a like a hubbub there in the 80s about it, maybe a bit too much hype. Probably true of one of our friends too. Per
Yeah.
Bach, famous physicist, worked at Brookhaven Labs, self-organized criticality. So now I want to throw, so these are the concepts that we need to try to answer your question of, can we get something out of this for cognition or, thinking and or, understanding behavior? In a nutshell, I'll try to just summarize, and then Mater, help me out. In a nutshell, Kelso, I got to
Awesome.
mention a lot. There's a lot of people I need to make sure I mention. Huge name in this field, right? Hawk and Kelso Boon's model. Metastability, the concept that if you're at the edge of chaos, you get these power laws, including one-ref noise. So there's signatures of being in this kind of state. And it turns out that the state is very useful for having a flexible adaptive dynamic where learning can happen, contextual effects can happen. You get memory and computational capacity out of one ref. So that would be like the Bertschinger, Notschlager, Kwok-Smith papers I was mentioning. So you get all these good properties that are related to one ref. And then now you have theories of cognitive function, neural function. Cialvo, famous neuroscientist,
Yes,
who's done a lot of work on this, right?
Beautiful papers by him, yeah.
Beautiful papers. So many names that I really, I'm sure I'm going to forget a lot. But so there's a big community out there, and it really is probably more established in the neuroscience community than it is in the cognitive science community to suggest that Victor Yersa, who worked with, has done some excellent work along these lines with metastability, who worked with Kelso, because they're dealing with data where they can really see the metastability. I think that's why. They're dealing with data where you can see patterns forming and reforming over time, and you got to understand that. Whereas those patterns are not so easy to see in reaction times or something, the kind of behavioral data that we get. You can, I'm not saying you can't, but it's just much more apparent depending on the kind of neural data that you have. And so I think they've been for a long time much more open to the idea of using these concepts and bringing them into neural function.
Right. So that's where we come in, like our experimental paradigms, like deeply constrained of how we can think and envision our data. So when we do experiments in laboratory where we have one outcome measured directly and we randomize the trials, there's no way we are actually thinking about dynamics and doing dynamics. Compared to when we record these long time series and even reaction time, long time series reaction time, we're able to see these things which are otherwise not apparent. Yeah,
that's right. And if I may, I need to, before I forget, and then we can move on, because you said multifractal, and I want to, and I'm so happy for the work that you're doing, Damien Steffen's doing, so many other people are doing with Espinilin. I might be mispronouncing his name. So. And to put a note on this is that one of the things that I think both Guy and I got ourselves over our skis, if you know this phrase. In other words, we got ahead of ourselves with this whole one ref idea, is that we were making claims about self-organized criticality that are not fully warranted if you only look at the one over f. But if you, so then one way to get around that or to get past that, I guess you could say, is like I just said, you can look at neural data, look at the patterns themselves. Okay, you can go down that road. But another road you can take is to start to do multifractal analyses and go beyond just straight up one over f, where you can start to make more strong claims from the data to the underlying processes.
And so, we are actually working on that. So you would love to know that the Wallenbachers et al.'s critique, where they came in and hit on one bias from multiple perspectives. We are working on two manuscripts, part 1, part 2, which will address all those criticism and basically hopefully put them to rest, at least empirically. Now it will come down to value and things like that. People won't change their mind, but at least empirically we hope to put those criticism to rest.
Excellent. I'm looking forward to those papers. Thank you. It's a great service to the community to do that kind of work, because again, some of their arguments, while I think they still just miss the forest for the trees type of vice versa, some of those arguments are still very narrow, but
Right.
on those narrow grounds, there's some validity to them. And
Right.
so, or was at least. But now
Right.
I think as time goes on, the evidence just keeps piling up. And I think, again, and I think a lot of the community, certainly Wagenmakers himself, I think it's fair to say, who I know and several times, is kind of walking away from that debate. And I don't know. Hopefully, work like yours and like ours would. I don't know if we'll ever convince somebody like Wagenmakers, but the new generation.
Yeah, exactly.
You often just got the folks whose minds are a bit more open as they come into the field and look around at what's available and say, okay, so now, there's all this work been done and it's kind of well established. And like you said, if we can show the value, if we can show what you get from this perspective, both in terms of generating ideas and experiments, as well as understanding the data that you have.
Yeah.
Well, I think ultimately, in the long game, I think there's I don't want to say we're going to win, but we're making progress. We're making progress. Let's put it that way. We're making good progress.
And we'll vindicate like some work as well.
Yeah.
So Chris, like your critical branching neural networks, something which I have always been interested in, and which seemed to be very important, at point. And you also have patents on that. So what exactly are critical branching neural networks, and how do they differ than traditional?
I do have a patent, but that's a weird side thing. We can talk about it. Okay. The short. So I'll come back to the patent thing. So how I got into that was a couple of things. I was at a conference. I met a person by the name of John Beggs, who is at Indiana University, physicist, who but also neuroscientist, and was working with Dietmar Plenz on the idea of neural avalanches. And I'm not sure if I knew about those before that conference. This is something called the Keck conference. I can't remember the name, but it's like they have a different theme every year. The Keck Foundation throws amazing conference, by the way, incredible. If you ever get a chance to go to a Keck conference, do it. They're really well organized. They're well funded. At least they were. Amazing people. And so met him there, and we started collaborating. The collaboration never came to fruition, but there's a long story. But that's when I got introduced. He was working on critical branching, and because he had data from multi-cell recordings of, I don't remember what
mostly
substrate he was working with. Might have been leech or
mostly macaques.
Macaques. I think he was they've done it in all sorts of systems now. He was working with Petri dish type of stuff where you keep a little piece of tissue alive enough to see it twitching. Sorry for the metaphor here, but you just get it alive enough on the Petri dish and you can measure avalanches, these bursts of activity.
Very similar to the ones in the live brain.
Yeah. Oh, for sure. Absolutely. It's just a matter of, what kind of your experimental preparation, but the results are the same. Exactly. The results are the same, which is that there are these neural avalanches. It's another power law. It's also direct. What I really loved about it right from the start was that the theory was already there, very simple theory of critical branching, to connect the power law to the computational importance and the metastability and the pattern formation and reformation, adaptability, flexibility, contextuality, blah, blah. All that stuff was already there. And I could just walk right into it. And so then took a long time, eventually start to relate it to one-ref noise as well. That's harder, but because I should say for the audience, a neural avalanche is more like earthquakes or something, where you're looking at a parallel distribution of some quantity and how frequently that quantity occurs, like how big earthquakes are or how big these avalanches of activity are in tissue and brain tissue and so on. So you're not looking at time, you're looking at a distribution of events and their sizes, let's say, or their durations or what have you. So to make the connection to a fundamentally temporal dynamical signature like one of ref it's there. I mean, it goes all the way back to the self-organized criticality and Per Bach. It was already there back then, but to do it now in this new framing of critical branching was, at least for me, not easy. And so there's some work involved in doing that. And so we worked on a model. I guess that's a we, meaning the royal we. Like, I worked on a model for a while there. Yeah, and but because but I want to say very much inspired by John Beggs and working with him, even though that didn't come to fruition.
Yeah.
So yes. Okay. Now I got to go where you went with the patent. So I'm working on this, and then I've moved to UC Merced. I think it might be my second year there, and Paul Maglio, who is at the time was a manager at IBM, but I knew him all the way back from UC Santa Cruz days. I'm married to Teenie Matlock, who's a professor in cognitive science at UC Merced. He's working at IBM, and IBM's putting together a humongous DARPA proposal on neuromorphic engineering, which I probably had never heard of up until that time. I'm guessing, I can't remember. But they needed a cognitive scientist. They needed somebody to help out with, hey, we're going to be building these chips, and the chips are going to be spiking neural networks, and we're going to simulate those spiking or emulate in hardware, which was amazing. Like, wow, you can do this in hardware at the nano scale, extremely low power, build these chips. And we need a cognitive scientist on board to help us with a big picture of like how we test them. And I could do that. I was a cognitive scientist of that ilk. It wasn't my specialty necessarily, but of course, I don't even think they knew. They probably didn't know. Maybe they did. I don't remember. But I'm already working on spiking neural networks because of critical branching. And so I see this as like, oh, this is an amazing opportunity. I definitely want to get on this team if I can, because they're going to be also working on spiking in hardware.
Yeah.
And I'm already working on, how to get that to work in terms of, neural avalanches and the functionality out of that. And maybe something can happen here. And so I was lucky enough to get myself on the team. I started working on more the testing, like how to put these chips through their paces in terms of their cognitive functions, right? That was my job as a cognitive scientist. But I ended up also building some of the circuits that we were used to demonstrate the computational capacity through critical branching and something called a liquid state machine, reservoir computing.
Yeah.
I know I'm throwing all sorts of stuff out there. Anyway, that's how that patent thing happened, was because I was working with IBM, and
so
IBM wants to patent stuff, and so
right. These networks are different than your silicon networks, right? The way the way the in silico networks work, the way we program, neural networks for like like with one or two layers, let's say, they're different than those.
They are different. They're well, at that time, so there's this chip they call True North, and it was, enormous engineering feat to get it to work at all, because there was metrics that they had to hit on the engineering side in terms of size and power, and maybe speed too, but definitely size and power. To do that, they had to sacrifice a lot in terms of what functionality those model spiking neurons actually had. So they ended up being incredibly simple, mostly linear with some thresholding.
So what was unique? Like, what were they trying to achieve with this? Like, what was unique about these chips compared to chips you already have?
Oh, it was the again, the size and power. So maybe 1,000-fold power savings. So in order to run one of these chips and get the same computation, now I'm going to fast forward years later after doing, they're able to show, because by the way, deep learning happened. In the middle of all this, deep learning happened, right? Like, oh, we didn't know that was going to happen. And so we ended up, and I shouldn't say they, because I was now I was off on the side doing this reservoir computing stuff. Right. They were able to show that we can basically wire up a deep learning network in these chips, and they'll run much lower power, not faster necessarily, but much lower power than if you had to put them on a NVIDIA, GPU or something like that. So that was the big win. There was always a sense of like, maybe we'll get some functionality beyond your standard neural network as well. I don't think that ever happened. Maybe Intel picked up the slack where IBM sort of let it go. Intel has been working on a Loihi chip, and it's got learning on board, and the other ones didn't even have learning on board. There's a whole. I don't know how much we want to go down that whole road, but they continue. That community is in its nascent, still in a nascent stage of development, I would say. There are definitely people doing great work on this, but it's like, if you think about we were talking about exponential, growth and takeoff in some of these technologies. They're still on that sort of floor, kind of, toiling away,
and not knowing whether it will ever
go boom. Right. It might not. I can't. I don't want to hazard a guess.
But coming back to the hope, right? Because the idea or the hope is very important, and it stems from the epistemological standpoint. It talks to the idea that brain works very differently than our currently, what we call computers work, right? So we need to get this route if we want to actually have intelligence of this kind, right?
Yes.
So that's the epistemological, viewpoint on that, and also from the standpoint of future innovations and the Moore's law, right?
Yeah.
We also need to kind of go beyond Moore's law. We need to go into these kind of avenues.
So I got to give a shout out to Todd Hilton, who is the program director at DARPA, who developed this neuromorphic engineering. It's called the Synapse. It's some acronym I'm not going to remember right now, but the Synapse program got DARPA to put huge money into this. And Mater, you just kind of gave his spiel. Like that was his spiel that he gave to DARPA and convinced them probably on the order of a couple $100 million to say, look, Moore's law is ending. Physical constraints, we're running up against physical constraints that are going to fundamentally limit what we can do with computer chips at this, going forward. If we're going to get past it, we're going to have to make a big change in how we even think about computing at the hardware level. Neuromorphic engineering is one possible way for us to sort of shoot past the limits that we're hitting. A quick aside would be like, I think that the issue of power is now becoming more urgent. Not that we have a solution yet, but it's becoming more urgent.
I mean,
because you've got these large language models, for example, and AI in general, that, it takes the power of a city to run some of these models.
So that's something which is, I think this power consumption of our technological needs and communication like we are doing right now, right? It's so couple of years back, I learned that when you watch a Netflix movie, you're burning like a bucket full of coal with all the transmission and everything, right? And I had some friends who were like very green, right? Like they would not wash their clothes for like 4 days to, save water or electricity. And finally they were into movies and they were into like almost everything, like full day, like screen viewing. And I was like, when I figured this out, I was like, what you're doing is not going to help, because we all would be consuming like 20 hours of videos at some point, So now it is becoming more and more apparent, and it's kind of something brewing which we have not even given attention to as a society, right? How much power we consume in just data, data transmission.
And if you talk to people who are on the bleeding edge of AI, they know this is one of the. It's coming up fast. In other words, it's not in 20 years we'll worry about it. No, in like 5 years, and like very soon we're really going to have to start worrying about this. I don't think anybody has a good answer, by the way. I'm not saying neuromorphic engineering is an idea.
Right.
I'm probably not qualified to say what's going on in Intel, for example, over the past few years. One of my students, Tim Shea, is working there, by the way. So, who worked on critical branching and then ended up going down that road, and they hired him, and he's doing stuff. I don't know. He's proprietary. I don't know exactly. Maybe that's going to be an answer. Maybe the answer will be something completely different.
Right.
I don't know, but people are going to start working on it.
And it's actually more than what you think, because for instance, I just bought a workstation, with like 32 cores, like 24 GB graphic card for my office, and that is a power supply of 2 kilowatt. So when it runs, and which is mostly running because I'm running simulations, it's like my room is having a 2 kilowatt heater always, right?
Exactly.
And then I also have to, lower the temperature of my AC to counter that. So I'm actually burning on two sides, to maintain the homeostatic,
to basically
survive. And
hey, Before we go past this, I also should mention, because I want, there's another reason why I wanted to give a shout out to Todd Hilton, is that he also started another program at DARPA called the Physical Intelligence Program. And the University of Connecticut, with Turvey and Jay Dixon and others, Bruce Kay was involved heavily, and I'm sure others names might be, Nigel Stepp, another person who was involved in that, were funded. They were funded by that program. And because Todd saw the bigger picture here, and I got to know Todd pretty well. We also did a little bit of a collaboration. He was a member, he was an advisory board member on one of our grants and stuff like that. And again, he was not, sometimes people think these administrators, these program directors, are like not intellectually engaged in the work and stuff like that. Well, I think I was, and I certainly say Todd Hilton was. Like he wasn't just running the program. He was also thinking about the ideas and where they logically would lead to. And if you go past neuromorphic engineering, you start to think even more fundamentally about the physics and the physical constraints on computation, on intelligence. You start to get into thermodynamics. And so the University of Connecticut folks have taken that very far and done some amazing work with some models, thermodynamic models of foraging, for example. Awesome, amazing. That derived from that program that he also started. That program, I think DARPA, it only lasted a couple of years type of thing. But if you ask me, it was ahead of its time. I know Todd has continued outside of DARPA to push on this idea of thermodynamic computing, which is maybe, again, so probably Todd and I see things similarly in that we can see the eco side. He funded University of Connecticut, but we can see the computing side, and we're willing to sort of think about computation, which is going to be at some level symbolic, and the two of those things together. And so he's continued that.
That's very interesting, because if you think beyond the debate of how the brain works, computational versus non-computational, and go more into the practical domain of we trying to compute in our life, with devices, then suddenly ecopsych becomes more important, or the dynamical ideas become more important.
That's right.
From the standpoints of energetics and and efficiency.
Absolutely.
and physical limits.
Yes, exactly. So and that was, thank you for making that point, because that's the point I wanted to make, was that with respect to ecological psychology, it's that framework that gives you an inroads to think about the physics and the thermodynamics of behavior. And yes, I'm willing to say cognition and the representational stuff too. But whatever, the point is, that's a framework, that's a way of thinking that gives you that inroads. And I don't think it's not available in connectionist modeling. It's not available, certainly, in a computational theory of mind that's purely symbolic, because it's so far abstracted from the physical world that everything's done completely with utter disregard to physics, utter disregard to energy. There's just nothing.
It's basically, if you can do the same computations with kind of vacuum tubes and silicon wafers, right? So we have not moved in some ways. We have advanced in certain ways, but in certain other ways we have not advanced, right? We are still stuck with the same idea of computation.
You sound like Todd Hilton. So I'm gonna give you a little bit more of what Todd Hilton would say. He often talked about the von Neumann architecture, which is huge, giant in the field, polymath, incredible thinker, one of the most brilliant people probably that ever walked the planet. But he did leave so many legacies. One of them is the very concept of hardware and software, which we take for granted. We just take for granted that that's how computers work, right? There's a CPU, there's a bus, there's memory that goes back and forth between the CPU. That was von Neumann, who was trying to solve a problem of, doing computations for work on the atomic bomb. So, by the way, brilliant guy, also very interested in intelligence and deep thinker, of course, but he also had this very practical, urgent need during World War II. But what we're left with is that divorce, which has been enormously helpful for the field to divorce the hardware from the software. But once you do that, that's the von Neumann architecture. It gives you license to just think completely in terms of the software, because and of course that's founded on a Turing machine, which
Yeah.
maybe your audience knows what I'm talking about here. Universal, and it's, and the whole concept is basically that you can do anything with this architecture as long as you don't care about how long it'll take or how much
Yes.
power it'll take.
So they're called rate basically rate independent processes, right?
Yeah. So,
Going back to
Todd Hilton will often say, we've been living with the von Neumann architecture and its legacy to this day, so much so that most of us don't even realize it. We don't even realize that that we're living inside that framework, and we need to bust out.
I give a very simple example of, like, your computer might hang for, like, Windows can hang for 15 seconds and you will still get, your screen. If you hang for 15 seconds, some animal will come and eat you by that time. So it's when you're talking about biology,
that's right.
That rate becomes very, very, very important.
Exactly.
Thermodynamics
Exactly.
Is very
exactly. And once you've made that divorce between hardware and software, it's very hard. I mean, if you think about it from an abstract perspective, if you look at a connectionist model, how would you cash it out in terms of energy consumption? Like, there's just no way to do it. They're completely disconnected.
But So do you think this is like a big void and a big field for future research, where we are searching for computation or adaptable behavior in the structure itself, or in the physical interactions themselves, rather than in an architecture?
I mean, look, the short answer, of course, is these are huge questions you're asking me, and I'm not qualified to really know. I will say that, let me start. I've been bashing the von Neumann architecture. Here's what's good about it, is that it gives you this ultimate degree of this ultimate flexibility
and
to
fidelity.
Take that machine and turn it into anything.
And fidelity as well,
And fidelity, exactly. So I think as we move forward, if we go back and think harder about hardware, which, by the way, would be like going back to cybernetics. I'm going to throw another word out at everybody, which interestingly is the roots. Probably can draw a line from some areas of cyber. Ashby and Ross Ashby to Gibson and ecological psychology. There's probably a way to do that. I mean, they were the animal machine sort of interface was very much, and perception action loop control systems. We're going to go back there. Is basically as we pull back from von Neumann and start thinking about hardware again, we're kind of working our way back to the cybernetics folks in some sense, which is going to take us closer to ecological psychology in all likelihood. But we can't lose sight of what the magic of the von Neumann architecture and the flexibility and the fidelity, like you said. So I don't, again, it's far beyond me. I don't know how we're going to do this. But
so, I mean, for the viewers, like, for instance, I can download the same Zoom in my phone, in my laptop, or on desktop, right? And you can also download the same Zoom. So that divorce between hardware and software allows us to have the same capability in different architectures, as well as reproduce across time and space.
Correct.
So, but maybe
nobody wants to lose that, right? Nobody's going to want to lose that.
So, but maybe in the future, for more specialized things, like, for example, you were talking about, we will have these chips, or we will have this technology which will be more neuromorphic, where we can exploit the structure or the physical interactions themselves for very specialized things. And we can capitalize on those in very domain specific in a domain specific manner.
And by the way, once again, coming back to ecological psychology, those specialized things, if you have to take a guess, low level perception, low level motor control, like those are probably going to be where the specialized hardware happens. Is that perception action kind of interface?
I see. So, for instance, correct me. So, for instance, we might have like these ganglion cells. We might have very low energy circuit, for instance, as something to control suspensions in cars, right?
Exactly.
Which are more dynamical aspects of operating a car, rather than controlling some of the more symbolic aspects of.
For example, yes, absolutely. I can give you a couple other examples. from Switzerland. The lab was I'm going to forget the lab. It's a well-known neuromorphic sort of center of neuromorphic computing over in Switzerland. And for a long time, before the IBM stuff, before True North and what I was talking about, that idea has already been around. For those of maybe if you've heard the word neuromorphic, you might have heard it in conjunction with Telluride, the Telluride Neuromorphic Summer School, which has been going on for a long time. So people have been thinking about this for a while before the whole IBM stuff. And in that community, where they've made the most progress is neuromorphic vision, neuromorphic audition. So neuromorphic models of the retina type of thing, or the cochlea. And so that would be another example of what I mean by really low level perception. And I think, they've made, and I haven't kept up, but they were partnering with the IBM folks, for example, because, hey, maybe we can get this True North hardware, and we can put our cochlea model in that hardware. And now you've got something that does some, I think it was almost like pre-processing of sound, but on the cheap, low power.
So in the sense, for instance, I mean, I'm just, guessing and, kind of being a visual thinker. We have these surveillance cameras, and we have this, like a very simple lens and the same video processing for almost everything. We could have chips just specialized for facial identification.
Perhaps as high, and that would be, of course, a higher level of perceptual function. Perhaps exactly. I would say start low, and then how could you build those chips up to the point where they are natively on. This is also called edge computing, by the way. There's a whole industry on this, right? Where you're doing edge, meaning away from the cloud, meaning out on your whatever your device is, whether it be the camera or the phone or what have you. Edge computing, often that's precisely where you have to really think about power, because often these are battery operated devices. And so you can't, if you want to do face recognition on your phone and not send the data to the cloud and have an internet connection, and well, you're going to have to do it on the cheap. You're going to have to, you can't run the kind of models that people run on the cloud. And it's not, again, it's not even necessarily like a memory or a CPU problem. It's a power problem. And so, yes, that would be the place where you would imagine some of this.
It's so interesting that a lot of things are full circle back, right? Like we went from localized computation to the clouds, and now we are trying to come up with solutions to get back to to local computing, at least in certain domains.
It is interesting. Yeah. I know, a shout out. So Mitch Waldrop is a science, Waldrop, WALDROP for in your audience. Great science writer. He's got an amazing, I don't know, it's not a biography, history of the Santa Fe Institute and complexity science. He's pretty famous for that. Like, I think the book is called Complexity. It's been I read it many years ago. Well, in 2018, he did another one. And in this one, he's focused on J.C.R. Licklider, who is at the center of the birth of AI, the birth of computers, and the birth of the internet. If you've never heard of him, it's kind of amazing. Like, there's this person behind the scenes who is at the middle of so much of the technological advances that we've experienced. And I'm just about done with the book right now. Great. Really excellent sort of history of all this kind of stuff. And you get the big picture of what we've been talking about, because it starts with von Neumann and Turing and cybernetics, McCulloch and Pitts and Norbert Wiener, and goes all the way through to ARPANET and stuff like that. Amazing.
No, a lot of times you read these books, and I have not read this one, but you see like these powerhouses, like these people, some of them, and it's like, how can they contribute so much and so significantly, not like just one, two, like significantly, like considerably different areas,
exactly. And I don't, I'm not going to call you out. I'm going to just say for myself, I have vaguely heard of this guy, Licklider, and I'm like, I've been in this field for 30 years. And I kind of heard that name once or twice. I had no idea. I had no idea how central he is to everything we're living with today.
It has always been the case, right? When you think of Edison or Nikola Tesla or, for example, Graham Bell, right? I mean, Bell did not just made a telephone; he made like so many different things. And likewise, we have similar kind of minds.
Exactly. Yeah. So anyway, I can't remember. That was a bit of a tangent, but
yeah.
but
So
yeah.
so Chris, what is the state of neuromorphic technology now? Like, are there academic labs who are working on neuromorphics within the US
Oh
as
yeah,
well?
yeah. Oh, for sure. Well, I mentioned the group in Switzerland, and
Yeah.
I'm sorry, I'm not going to try to look it up while I'm on Zoom and on the
Right. Yeah.
podcast. But there's a group in Switzerland. Toby, names might come to me. It's been a long, it's been many years since I've interacted with those
Yeah.
folks. So there's a group in Switzerland. There is in Irvine. There's a young guy who's, I don't know if he's still at Irvine, who's been working on this. There's Ralph Etienne Cummings, who's a pretty big name. So again, you can see I'm only partly facile with this
Yeah.
community. I mentioned Intel. Intel is, I don't know where it's going to go, but they put quite a bit of money into this Loihi and now Loihi 2 chip.
Okay.
I mentioned a graduate student of mine is a former graduate student is working there, Tim Shea. So there is a community. Like I said, they're nascent. They're kind of, there's names that I kind of know, and I've interacted with that community to some degree, but not a whole lot. I've been to the Telluride Neuromorphic School one summer. I was there for at least 2 or 3 weeks or something like that. And I think it's, I don't know if it's, well, I think right now, deep learning and then of course large language models have kind of taken center stage of, and I wonder, are we going to have a period now where people are going to forget for a little while about all the power issues that we've been talking about, and just go, forget that. I got ChatGPT, and that's all I care about. I being like, the industry, the world. And so for a little while, we're probably going to. You're asking me these big questions. I don't know, but if I had to guess, it's going to draw attention away from the neuromorphic community for at least a little while,
right?
Until these power issues really become pressing, and then we'll see.
Yeah, and also there's an incentive for that in the free market, to work on those issues. That drives a lot of thinking and innovation as well. Yeah. Right. So Chris, where are you right now with your research? Like, where is this going for you?
Yeah. So part of it, I am still very interested in the idea of much more efficient models of intelligence. I am pulled myself away from the constraints of a spiking neural network. Through that experience of working with IBM and all those folks, I should say I also worked a little bit with the Intel folks through Accenture Labs. That's the Tim Shea thing. I find that it's too constraining, and we don't know enough about, again, just my personal opinion. We don't know enough about how computation is really implemented to sort of put all our money on spikes, because spikes in and of themselves, sorry for your audience, action potentials of neurons. In theory, a spike could be quite efficient because it is an event driven. In other words, power is only expended for the most part. And this is not, I'm not talking about real cells here. I'm not talking about real brain cells. I'm talking about in the neuromorphic hardware. Is only expended at the moments when the spikes are generated. And otherwise, it's kind of quiet and passive. And so you can see why that community went spike-based, because it inherently is potentially efficient. That said, you got to figure out how to actually do stuff with spikes. And that has been very difficult for the computational neuroscience community for a long time. I do remember a lot of, again, I shouldn't name names here because I don't want to, try to say that I know what they're thinking, but a lot of people on that, big name people who were not only on the DARPA team I was on, but on other DARPA teams, HRL was one, we're all sort of questioning, do we even think that spikes, we can really do anything with a spike, computationally powerful enough? So I'm convinced for now, I don't know, at least I personally don't know what to do. So I've been working, when you're asking me, what am I doing? I'm working on a model that is also looking at, in this case, prediction, because, we certainly one of the things we've learned through cognitive science, through ecological psychology in terms of strong anticipation. So again, I associate, for example, not only Damien Kniesel-Stepp, Turvey himself, that which to me simply means anticipation is like a non-representational way to say prediction, whatever. Again, I'm not going to. For me, I'm a
Yeah.
little bit agnostic about that. But what I think we can agree on is that it's a fundamentally key and important
Yeah.
aspect of cognition. Of course, we have something called predictive processing, as Andy
Yeah.
Clark, and all sorts of, and the Bayesian camp, and
Yeah.
so everything's. And if your audience doesn't know, ChatGPT and large language models, many of them generate through prediction, through autoregression, and just sort of successively predicting the next word, the next word, the next word. So prediction like this keeps coming up and so clearly fundamental. I'm interested in hardware that is fundamentally built to do time series prediction, basically.
Very
So,
interesting. Very
so I don't
interesting.
know, and I've got some code
Yeah.
working and stuff. It's not prime time yet,
Yeah.
but that's my fun pet project that's kind of
R-
going on when I have some free time.
Right. I mean, and it's hard to imagine, like a psychology professor would be so deeply engrossed in building hardware
Well, yeah,
for this.
and I'm
Yeah.
not building the hardware. I'm doing the software, but
Yeah.
the
But yeah.
point is, you can emulate it. And so one of the things I
Right.
learned, I'm sorry to interrupt you, Mater, but one of the things, and I'll let you speak in a
Yeah.
second. One of the things I learned is that from DARPA is that, and IBM in particular, is that if you're going to go digital, and there's all sorts of you can always go analog, and
Yeah.
that's a whole other can of worms with that.
Right.
But if you're going to go digital, you can always work in the software as long as you know how you can
How
emulate,
to
how you
implement,
translate that
yeah, and
to the
implement the
hardware.
hardware constraints, yeah, within
Just so nobody
software.
thinks I'm sitting there in a lab with a soldering iron and tinkering with stuff. I'm not. I don't know how to use a soldering iron. I probably burn myself, but
No,
I do have a sense of this code. I can imagine how you'd
no.
build
I think
specialized circuits that would be efficient. Yeah.
I think our viewers are at a stage that they know that before Boeing actually flies a plane, Boeing has already simulated the plane in the hardware.
That exactly, and
Yeah,
and that's exactly what we did, by
yeah,
the way,
yeah,
on the IBM team. Is that everything? It was MATLAB code. It was
yeah,
actually emulated MATLAB code that was one for one with the hardware, and so all of us were working with the MATLAB code. We
yeah.
weren't, and then the engineers were working on the hardware, and you had to divorce that because we couldn't, we couldn't wait for them to
Right.
build stuff so we
And
could
and,
test it.
and, and that's the beauty again of the one Neumann architecture is, it allows us to
Yeah,
simulate hardware on software as well, for different purposes.
yeah, yeah.
So that's where
So
you are with your,
I'm working on that. I continue to work, and then about this stuff. I continue
yeah,
to work on the 1 over F, and now
yeah,
I'm trying to get more theoretical, and building, taking that idea that I've run with for a while now on the empirical side, working with hierarchical temporal structure, and now more a model of that
yeah.
that I think makes some interesting connections to hierarchical structure and processing in general. So that paper hopefully will come out sometime before I retire. Takes forever. This process is taking forever on
Yeah,
this
and
paper, but
these days, in general, it's getting harder to find reviewers. Papers have been under
yes,
review for 6 months.
yes. But
Yeah,
that's probably, I don't know where that'll go after that. But I'm excited for that paper, and it feels to me like a little bit of a culmination of a lot of that work.
right.
Maybe it's not like the end necessarily, but it's certainly a culmination
Yeah.
of
For
a
for
lot
the
of thinking and a lot of work over the years.
right.
So that'll be exciting when that
I'll
comes out.
post the link to your preprint, in the on YouTube videos.
Great.
Yeah.
Oh, thank you.
For this particular article. So before we wrap today's episode, Chris, what's your advice given your career trajectory and fascination with both the academic and the more applied aspects of your science? What's your advice? Some of your tips for graduate students and young academicians like myself.
I mean, so I'm going to give you more of a sociological type of answer, because I think it's that's when I, and may I say for just a moment, so when you mentioned I was a chair, I was actually dean of the graduate division for 4 years. I was chair of our graduate program, but I'm not chair of the department. But and who cares? I'm done with that. It was again, that's a side thing having to do with being an NSF, coming to a new university. They need administrators. I know something about administration. Great. Come, please help us run the graduate division. Okay. But in that role, I would answer this kind of question all the time, because I'm the graduate dean, and PhD students, and I was also dean over the postdocs too. would constantly be, coming to me personally, or just the graduate division in general, asking for all sorts of advice, right? And I mean, the world has changed in huge ways since when I was a graduate student to now, or when I was an assistant professor and you're an assistant professor. It's a different world. So, I mean, you know, building an identity for yourself in the world of research is just paramount. It is just, and it's something that I've played with my identity. So you asked me, don't take my advice. Like, there's a part of me like, don't do what I did.
Yeah.
Like I developed an identity and then I changed it. And I learned a lot. I enjoyed it. I would never take back what I did, but it certainly had a major impact on my development of, if you're talking about like my career type of thing, right? Because people in our world, it's easy when people understand who you are. You are this person, and you develop that identity, and you become. So I don't think it has to be siloed. It doesn't have to be like the narrow expertise like we were talking about at the beginning of the conversation. But you do need an identity, and it's just so critical. And you need a community, and so. And if you're already there, Mater. You're past this. I'm talking more PhD students now, and maybe postdocs too, right? If you're an assistant professor, that means you're probably not going to get an assistant professor job unless you've already done this to some degree, right? And so I'm giving maybe advice a bit more a little bit earlier in your career. Work on that. Constantly be mindful of what you're doing, your networking. Multiple mentors is critical. I've mentioned a lot of people who are my mentors. There are more that I didn't mention because I just didn't have time. I would say to anybody, have multiple mentors if you can. Work with teams. Science has become more collaborative in general. We used to have a model, depending on the field, where it was sort of the lone, researcher climbing the mountain type of thing. Those days are mostly gone, at least in cognitive science. And so work on those networks and those collaborations, and in doing so, always be mindful of who you are, in all of those different collaborations, so that, when you go to submit that paper, when you become a journal editor, when you get that first grant, again, people see who you are, they know who you are, and they can go, I know who that person is. I can put that person in in a frame that makes sense to them. There you go.
So
it's a sociological type of answer.
And a related sociological question, which is so these days it's a little harder to recruit talent in grad school. So a lot of people, because there are more easy ways of making money, ranging from having a TikTok and OnlyFans to do side hustles, and things like that. And also the technology industry has grown so much that one, depending on the skill, whether the skill is more multimedia related as skill or more quant skill, more programming and more hands-on with coding, there are more opportunities outside academia, and they are also lucrative to begin with, right? So why should somebody choose a PhD in the current environment with high inflation, high cost of living? You will be spending 5 years with like 30K salary, 35K, compared to more lucrative early options. So what's the benefit of actually doing research? What do you think for a young person right now?
Okay, so I mean, part of it is it is a bit of a calling. Okay, so let's just be honest. It was certainly that for me, and back in the day, it was just people who were interested and just couldn't imagine doing anything else, and those are the people who ended up as PhDs and ended up in academia. So I don't know. I think some of that has still changed, in that you just have to be like so driven by wanting to be a researcher. There are some people who are very interested in being in the club of being a professor. That was never me, but that I think that drives some people. Like the persona of a professor is what they want. Okay, that's another reason. But maybe I know that's not where you're going. Like at Merced, I think we've got a pretty good track record of our PhD students going on to both academic and non-academic jobs. It's probably a quarter to a third of them are academic, and then the rest are non-academic. And they are very the specifically Silicon Valley, okay, it is the tech industry that tends to really want our students and pay them very well with their PhDs, because they want somebody who can lead a project, who knows what it means to put together an idea, a proposal, think it through, and then execute it. Their time scale will probably be much faster than a PhD. PhDs over like, the whole thing is 5 years, but let's say the dissertation is like, depends, 2, 3 years, whatever, right? Well, they're going to probably be on a 6-month time scale or something like that. But the same type of way, the ability that PhD students have learned to take a project, see it through like that, that's very valuable.
So there are certain skills which only a PhD kind of environment provides you, right?
Correct. So if you're looking at it from a skill-based perspective, which I think is where you're going, not only the coding, look, because you can get coding, you don't need to get a PhD for coding, right? So, and the stats, you probably don't even need a PhD for the stats.
It was a very ugly question, from a scientific and from that perspective. But also, given that I want to, be able to, for the viewers, especially the young ones, to see the value in a PhD, and you are probably the best person to, to reflect on that.
Well, there's my simple answer. And again, and I think it is, and it's also, by the way, it's all those things, and like a lot of our I mentioned Tim Shea, Brian Kirster's another student of mine who's working at Facebook, has been at Facebook for a long time, or Meta now. And we got people at Netflix, Google. They are also, not only is it that, they're good at projects and big thinkers, but they're actually doing work that's relevant to their PhDs. They're doing work, often it's, for example, with Tim Shea, it's neuromorphic computing. With Brian, he's doing data science that is definitely using some of the both modeling and statistical skills that he picked up specifically as a PhD student that translated into what he's doing at Meta. So it's not just that broader, hey, you know how to run a project or something like that. But in many cases, they really are looking for people with the kind of, especially modeling and statistical skills. And we can never forget, communication, writing and presenting. That's ubiquitous, right? Doesn't matter almost what profession you're in. You got to be able, and PhD students are, in all domains, not just cognitive science or psychology.
Trained for that.
You just get good training in that.
And so, more than that, if you find fascination with intellectual, in general enterprise, you would have the most interesting set of friends, throughout your life. Ranging from like a young undergrad to 80-year-old professors.
Exactly.
So thanks, Chris. It was a great conversation, and I myself learned a lot about a lot of these interesting areas, especially neuromorphic computing.
Thank you so much, Madhur. I really enjoyed it. Again, I'm honored that you invited me on the podcast, and I hope your audience enjoyed it as well.
I sincerely hope so as well. And I'll put all the links you mentioned about different research groups and publications, your own, in the description in YouTube.
Thank you very much.
Thanks, Chris. Have a great day.
All right.
Bye-bye.
Take care.